Section 11.3 is partial derivatives. It's kind of a fun section where we'll learn to take derivatives of functions of several variables. We'll start with functions of two variables. X and y is a function of is the argument of a function f, and we'll define the partial derivative with respect to x at the point AB through the following limit of a difference quotient, something we're rather used to. So the derivative in the x direction, or with respect to x at the point AB of f, is the limit as h approaches 0 of f of a plus hb minus f of ab, all divided by h. This is the same difference quotient that we've always used in calculus. Notice we just clipped off the b's here, we'd have just the derivative in the x variable of the function f. So we're holding b constant, and that's the theme of partial derivatives in general, is whatever variable you're not taking the derivative of, this is the x variable, we are taking the derivative of it, the one that you're not taking the derivative of is held constant, and we essentially do nothing in that component. We treat the components in the variables in the second component as constants. They don't move with respect to the limit. Okay, similarly, the partial derivative with respect to y at AB is a similar difference quotient. Now a is constant, we have b plus h and b in the arguments of f divided by h as usual. And the process will be really similar. We'll have a lot of the same differentiation rules that we had in Calc 1. So that's really nice to have around. We can also generalize this from being at a point AB, each of these partial derivatives, to a function f sub x, or the partial of f with respect to x of variables x, y. So this is what we did in Calc 1. So the necessary conditions for that to be the case is that the partial derivative with respect to x exists for all x values in a neighborhood, or some open set of a. Okay, so all around the point a, or the x value a, the function is derivative, or the function has a derivative, or it's differentiable. In other words, this limit exists within that neighborhood. Then we can talk about a function f sub x, or the partial of f with respect to x of the variables x, y is equal to, again, this difference quotient. So what that means is we can calculate partial derivatives of the function f just like we did with derivatives, and come up with a new partial derivative function, just like we came up with a derivative function in Calc 1. So let's have a look at an example. And we'll start doing that essentially right away in the examples. So we're asked to find the first partial derivatives of a given function. And we have f of xy is equal to x to the fourth y cubed plus 8x squared y. And we're asked to find first partial derivatives. So f sub x of xy, we'll use our partial notation. Some of these are listed at the bottom of this page. We'll look at those in a moment. So this is the partial derivative with respect to x of whatever comes to the right. It's just like d dx before. Call it partial d dx. And our function's here. We're going to operate on it with that partial derivative function. Now remember this. Well, we don't have to remember it yet. Let's first see, we're exhibiting linear properties of this partial derivative operation. That is inherited from the limit. So the limit of a sum is equal to the sum of the limits, provided the limits exist. So we're going to split things up as we always did for derivatives. And again, that's coming from the limit laws. Also, product rules could be used as well. But note that what we're going to do in here, we're going to treat y cubed as a constant and this y as a constant. And that's because our partial derivatives are with respect to x. So this is really kind of an easy derivative. It's what students would have wanted the derivative to be back when you learned implicit differentiation. You just ignore the other variable and take the derivative with respect to x in this case. Okay, so the result of that is 4x cubed, and then times that fixed function of y, or fixed y term. 16x times that fixed y. Simplifying this, well, that doesn't need any simplification. That's just fine. 4x cubed y cubed plus 16xy. Next, same derivative, but with respect to y. So we start over, partial d with respect to y of the same function, f. And now we hold the x variables, or the x terms, constant, and take the derivative with respect to y. In this case, we get 3y squared. In this case, we get 1. That handles that. Rearrange terms, clean this one up. We end up with the following answer. Pretty straightforward process. Again, it's that sort of, it's what you wish the implicit derivative was back in Calc 1. And it's the mistake a lot of students made in Calc 1. So another example to exhibit these properties a little bit further. Find the first partial derivatives of f of xy equals x to the y. Okay, so again, first partial derivatives means for every component of this function, we have two components, x and y. So I'll have the first partial with respect to x, given by this. And this is just a power rule. If f is equal to x to the y, then y is a constant with regard to the partial derivative x. So we just essentially do the power rule. Y minus 1 in the exponent times that y that comes down from the exponent. So that is following directly from the power rule. I'll even make a note of that. It's power rule. Okay. If that was an implicit derivative we were taking, it'd be a lot messier than what it is. Okay, now next, the derivative with respect to y. Okay, now recall that our function has base x. So x is now the constant, y is the variable. So this is an exponential derivative. And if you recall from Calc 1, that an exponential derivative with constant or base a raised to the variable power x has derivative a to the x natural log of a. You can do that with implicit differentiation by setting y equals a to the x, taking the natural log of both sides, differentiating that, solving for y prime in this situation. You come up with this rule, or you just remember the rule as we have it. Okay, so if x is the constant, it's playing the role of a, so we have x to the y, or x to the variable, times natural log of x. Just as we, again, x is playing the role of a, and y is playing the role of x in this identity off to the right. Now at the bottom, just some notation. This is for a function z equals f of xy. We'll have several different ways to write this. This is what we've seen so far, but we might be a little more shorthanded at times just to save some work, especially if we're going to write that as a function of x and y. It's going to be possibly contextual from the problem, which variables we're talking about in terms of x and y. Partial f with respect to x. Partial up with respect to x of the function f of xy. We've used that notation a little bit already, only we had brackets in our situation, which is fine, with or without. F1 refers to partial in the first component, in this case the x component. D, capital D1, this is the partial with respect to the first component, partial with respect to x. So several different notations that we might see. And there's a lot of context for some of them. So just so we are aware of that, that box is provided. Now, to get a little bit more deep into this, into the use of these partial derivatives, let's take the partial derivative of a function at a point, or both partial derivatives at a point, interpret these numbers as slopes, and then we'll try to illustrate this with a sketch of the graph with the two tangent lines in it. This is better done in the textbook examples in section 11.3. I'll do it here and talk through it just so you've got that component to it, but the drawing's just not as good. So let's get started with it. Our function is this. We need to take the partial with respect to x and the partial with respect to y. So first, with respect to x, we'll hold y constant and take the derivative. Well, remember, this outer function is to a power of positive 1/2. We're going to need a chain rule because we have an outer function and then an inner function underneath that radical. The derivative of the outer function, 1/2, comes down from the power of the radical, writing that as to the positive power of 1/2. We subtract 1 from 1/2 to get negative 1/2 in the power. We write the inner function, just in that, this is g prime of f of x, where this is our f of x on the inside, and times the derivative of the inner function. That's the derivative of this function here. Of course, that's negative 2x, and this is minus 0. Note that that's the case because y is constant with respect to x in this partial derivative process. So there's less work to do here. You just have to remember to treat y as a constant. So we get negative 2x minus 0. Summarizing that information and cleaning it up, we move that negative 1/2 power to the bottom of this expression as a denominator, and we have the function we have for f sub x. Now, at the point 1, 0, what we're actually asked for in the problem, we will just evaluate this by plugging in these values for x and y. Plug in a 1 for x, a 0 for y, and we arrive at negative 1 over root 3. Okay, so that is, when we consider this, that is the slope of a tangent line at the point 1, 0 along the x-axis. So in the x direction, so as we move underneath this surface, if we move along the x direction, at this point 1, 0, the line that's tangent to the curve that intersects, or the curve of the intersection of y equals 0 in the xz plane, this is the slope of that tangent line at the value x equals 1. Okay, we'll have a drawing down below as well. Okay, so it, in the x direction fits the fact that we took this partial derivative with respect to x. So that's the one thing we really just key in on, and that makes this process somewhat easy. Now, similar for f sub y of xy, partial with respect to y. Same outer derivative because we are taking the chain rule, so we arrive at this term. Now we take the derivative of the inner function, and we get negative 8y from that times all this. Again, we treat that as x squared and the 4 constant, and those are just 0 in this partial derivative process. Cleaning this up, simplifying, we get a function that looks like that. And we need to evaluate that function at 1, 0. When we do this, we arrive at a value of 0, plugging in 1 for x and 0 for y. And this is our summarized partial derivative. Now interpreting that, we're along the y-axis. So it's the tangent line at the point 1, 0 in the y direction. It has slope 0. So the slope of the tangent line at 1, 0 in the y direction on this surface, whatever it is 0. Okay, so what is this surface and what do these tangent lines really look like? So here's the attempt at this down at the bottom. Again, the textbook has very nice drawings of this and a very similar explanation. So first, let's call our function z and then see what kind of graph we get out of this in three-dimensional space. And right about at this step, squaring both sides and adding the x and y terms over to the left, we realize this is most likely going to be an ellipse. It's x squared, y squared, and z squared with positive coefficients. All added up equal to a number. And sure enough, by the time we get here, we realize this is the standard form of an ellipsoid, and we can move from there. So this is an ellipsoid, and at the point xy equals 1, 0, we get a z value of root 3. Okay, so that might be interesting to note. And really, we have that plotted in our point over here. We know this is an ellipsoid. We try to mark out what the major minor axes of each of the cross-sectional ellipses are. So here we have the ellipse trace that's in the xy plane, and then we have another ellipse trace that's in the xz plane. We didn't do the yz plane just because it's hard to see. But you'll notice that this one has minor axis 1 on the y-axis. That's fitting what we have here, and then minor axis 2 for each of those. And you can see that that's actually taken care of in that drawing, at least somewhat roughly. Now the point 1, 0, root 3, well, we found that root 3 for the z value, so we know exactly where this point should be in space, and it's roughly represented on the graph right here. We're at a value of 1 on the x-axis, about root 3 on the z-axis, and 0, because we're in the xz plane, on the y-axis. Okay, so we've marked our point off, and now these tangent lines that we came up with, the one along the, as we move along the x direction, we've got a line that's generated as the line tangent to the trace curve that's in that, that's a parallel with that x-axis, or coplanar with that x-axis. Okay, and that thing has slope m equals -1/√3. That's what we calculated above, so we've input that. We've kind of tried to sort of roughly represent that slope correctly in the picture. You'll notice that this is the negative x direction, this is the positive z direction, so this slope is in fact negative, as it should be. So that's a nice consistency to note in the problem. It's about as good as the picture is going to get. Now, at this point, 1/0√3, we're also moving this way, and this is actually in the plane x equals 1. So this point is above this value, x equals 1, and this horizontal line is, it has slope m equals 0, and that's exactly what we calculated above. We sketched it as we have it. If this is sort of a, you know, it's an ellipsoid, so it's a flat surface, or it's a rounded surface, but we imagine right at this point, at the very top of it, it's got a flat point, sort of a top of the hill or top of a ridge on this ellipsoid. That's just descriptive language to try to see your way through it. Again, the book really has a nice, much better set of pictures for this, but this is worth it just to talk through it one time. Okay, also some of the subcurves. In red over here, we've described what these smaller curves are, right? At x equals 1, that's coming from this point, this value right here. The resulting curve from our overall function is the following. We know that we have an ellipse in the YZ plane with minor or major axes, whatever values we might come up with. And notably and interesting, at y equals 0, coming from here, we have a circle. So when we look in the y equals 0 plane, we know that that's this y equals 0 trace, which is the xz plane. We have this circle sitting going in and out of the page for this. Just to note a little bit more about what this surface was using traces. Okay. Now, functions of more than 2 variables. Well, there's not much more to do here, which is nice. So we define things quite the same. The derivative with respect to x, or the partial derivative with respect to x, of a function of 3 variables, x, y, z, is defined as the limit as h goes to 0 of x plus h. We hold y and z fixed minus f of x, y, z, all divided by h. And again, this one will be a function if this limit exists in a neighborhood of the point x, y, z, or the x value that we're given right here. Or a disk we might talk about in some cases, or just an open set containing x, y, z. Anyway, we don't have to worry too much about where and how it's defined. We'll see more on disks later, and let's just use this. So we'll calculate these partial derivatives just the same way we did for 2 variables. And f of x, y, z, if it's equal to this function here, given in the example, we're asked to find the first partial derivatives. Well, we have 3 components, so we'll have a first partial for each component. So carry that out. And we've got, with respect to x, we just differentiate the x variable in that function. It becomes a 1 times sine of y minus z. Sine of y minus z is just a constant times our derivative, so it remains as is. With respect to y, now we have an outer function of sine, so we take the derivative of sine, and we get cosine of y minus z, and x is just a constant, so we end up with x cosine y minus z. Okay, oh, don't forget there's also a chain rule, times 1, that's taking the derivative of this inner function with respect to y. Z is a constant, so it's 0 plus 0, times 1 plus 0. Okay, and lastly, we have with respect to z, again, the outer function in this case is that sine, so we get cosine of y minus z. X is just a constant in this problem, so it remains as x. And then the derivative of y minus z is 0 minus 1 with respect to z, or the partial derivative with respect to z. So we get -1, and that's what makes this expression negative in the end. So it's that straightforward. You hold the other variables constant and treat them that way as you take derivatives, partial derivatives with respect to each component.